Thrombocytes or platelets can round off our formed elements. We've already gone through red blood cells, erythrocytes, we've gone through white blood cells, leukocytes. Now it's time for platelets, the thrombocytes. Now, these platelets are going to be found and originating from the megakaryocytes. Number-wise, while the white blood cells were under the 11,000 mark, red blood cells were anywhere between 4 and 6 million. Thrombocytes or platelets fall in the 150 to 400,000 range. So it's in between the two. Not nearly as many as the actual red blood cells, but a whole lot more than the white blood cells. Now, these platelets, their granules contain serotonin. Serotonin is helping maintain vasoconstriction. Now, the reason that's important is if you constrict the vessel, less blood flow is passing through. So if there's damage, you can help to try and constrict to reduce the blood flow to the damaged site. You then also have prostaglandins. Now, these prostaglandins are going to activate further clotting. So it's helping to create a snowball effect where it increases more and more clotting factor, therefore preventing blood loss. And the third one is ADP. Now, with ADP, I want to say, hold on, isn't that the one less phosphate from ATP? Yes, ADP, adenosine diphosphate. It helps the platelets adhere to the sites of injury or to themselves. So it helps build that clot up to prevent blood loss. So these platelets contain a few things in their granules that are important in the process of clotting and preventing blood loss. So what's the purpose? Obviously clotting. We've mentioned that. Now, there is a limitation to the clotting though. If you have a huge gash and blood's just pouring out, platelets might not be able to really stop that on their own. So there's a limitation of how large of an injury, how large of a damaged site platelets can work on their own without something being covered for compress or for stitches holding it together or whatever else. So they're great at working their magic, but they have limitations. Now, what's interesting is platelets that are not involved in clotting. So let's say you don't have an injury. Everything's working fine, you're healthy, no cuts. Those platelets are kept inactive by prostacyclin. So you naturally produce this in your body. It keeps the platelets inactive unless a stimulus is received. The stimulus would be a cut, an injury, an abrasion. So otherwise, they simply just keep flowing on through and not causing any problems. Now, thrombopoietin, we've mentioned that before. Thrombopoietin is the stimulus that causes the megakaryocytes to produce platelets. So, thrombopoietin. We've seen this before. We've gone through it. We're focusing on this side over here, right where you have the platelets and the megakaryocytes. But let's look at a little bit more detailed view. We'll add one more piece into this one. So we start with the hemocytoblast. Now that hemocytoblast goes to the myeloid cell into the megakaryoblast. Again, blast, not mature, still forming, still developing. From there, you go to the pro-megakaryocyte. It's almost there, but not quite. From the pro-megakaryocyte, you go to the megakaryocyte. The megakaryocyte is the final product. That's the final cell. It's from that megakaryocyte all these platelets will be broken off of. Remember, platelets are just a fragment of the megakaryocyte. So all these platelets in your blood are broken off of the different megakaryocytes in your body. All right, this one, I'm going to throw up big screen here. So first off, in hemostasis, you're noticing there is an injury. Anytime there's an injury, whether it's either just the endothelial lining of the blood vessel being damaged or the entire blood vessel ruptures and blood gets out in the tissues, it always has the same basic idea starting off. You have a site of damage, you then have a vascular spasm. Notice how in the vascular spasm, the blood vessel constricted. Remember, that was due to those granules of the platelets. That vascular spasm helps to close things up a little more, have less blood flowing to the damaged site. Well, with that vascular spasm being caused, then the platelet plug is being formed. The platelet plug now are going to be these platelets starting to group and bind together. They're kind of sticking to each other. They're sticking to the walls of the vessel. This is made easier for them because the vessel is currently smaller. So you basically create this smaller vessel by constricting to make sure this platelet plug can be formed. Now, as that platelet plug forms, those platelets are constantly having a positive feedback cycle. Their chemicals stimulate more platelets to be formed. They're going into the clotting process or the coagulation phase. Coagulation is going to take different chemicals like fibrinogen being converted to fibrin. That's going to help link all these platelets, create this network that will not just be platelets, but you'll trap red blood cells, you'll trap proteins, you'll trap whatever you can trap. So from the injury to the vascular spasm, to the platelet plug formation, to the coagulation, this is hemostasis. Now in that coagulation phase, so at the end of hemostasis, the coagulation will start with the prothrombin activator being formed. This prothrombin activator has one purpose: to convert prothrombin into thrombin. That's it. So you start off making this prothrombin activator for the sole purpose of converting prothrombin into thrombin. Now, why is thrombin important? Thrombin is going to catalyze the joining of fibrinogen to fibrin. So it causes fibrinogen to be converted to fibrin, which allows the fibrin mesh to be made. That fibrin mesh is what traps the red blood cells, the platelets, the white blood cells, the proteins, traps everything, making a nice solid structure to prevent blood loss. So you go from prothrombin being made, then prothrombin causes the prothrombin itself to be made into thrombin. Then you have the prothrombin being catalyzed, fibrinogen to fibrin. So let me show you how that all works together. I'm going to throw this up full screen. Now, if you notice, we have phase 1, 2, and 3. Now, phase 1, you can see a lot of different factors. You have the intrinsic pathway and the extrinsic pathway. The intrinsic pathway is when only the endothelium becomes damaged. So the tissues around that, think collagen and the rest of the blood vessel, are exposed to blood. In that intrinsic pathway, you can see that you then have going from factor 12 to 12A, from 11 to 11A, and you keep going back and forth. But then you have the extrinsic pathway also. Now, the extrinsic pathway is when any tissue around the blood vessel ends up coming in contact with blood, which means not just the endothelium was damaged, the entire blood vessel was damaged. So the blood goes into the tissue, which then comes in contact with tissue factor. That then goes through its cascade, heading down to the bottom of phase 1. Doesn't matter if it's extrinsic or if it's intrinsic, by the time you hit the end of phase 1, you are looking at the prothrombin activator. Now that prothrombin activator is going to then come up here and catalyze the reaction. It causes prothrombin to be activated into thrombin. Now thrombin is going to come over here and cause fibrinogen to be converted to fibrin. That fibrin is what creates this cross-linked fibrin mesh, basically the clot that you're forming. So you have a couple different things going on in these pathways. But also notice how often calcium is being used here. So just like we talked about back in AP1, calcium was in the bones, calcium was in your muscles because of the nervous stimulus there. Calcium was in the nervous system. Calcium is also found in the clotting mechanism for your blood. So again, calcium is also quite important here. But the whole entire clotting process, all these factors, all work together. any single one doesn't work, we're in trouble. But noticing from phase 1, you have the prothrombin activator, takes prothrombin and activates the thrombin. Then that thrombin can activate fibrinogen into fibrin from 1 to 2 to 3. So phase 1, phase 2, phase 3. Now looking at these individual clotting factors, some of these clotting factors, we've talked about the names already. We've already gone through them several times. Things to kind of remember. Clotting factor 1 was fibrinogen. Obviously, we talked about that. Converts fibrinogen into fibrin then. We talked about prothrombin going into thrombin. We talked about tissue factor for the extrinsic pathway. So that's factor number 3. Factor 4, calcium ions, we found those throughout the entire process. Factor number 5 is proaccelerant. That's both an intrinsic and extrinsic pathways factor. Factor number 6, I have no idea why, but that's not used. So factor number 7 is going to be proconvertant. This is going to be an extrinsic pathway only. Clotting factor number 8 is going to be antihemolytic factor A, intrinsic pathway. So anti-factor A. Number 9 here, we're looking at antihemolytic factor B. Now, antihemolytic factor B is also an intrinsic pathway. Now, if you notice, both A and B here are hemophilia A and hemophilia B, clotting factor deficiencies. Number 10 is the start prower. This is intrinsic and extrinsic. Antihemolytic factor C is also a source of hemophilia C if it's not working properly. Number 12, looking at the Hagman factor, that is going to be intrinsic. And to round things out with 13 is the fibrin stabilizing factor. That is stabilizing fibrin into fibrinolysis. So it basically is helping out that process at the end of everything, which we didn't talk about yet. So 13 different listed factors we have here. This is a micrograph looking at what a clot is when it's all intact, once all those factors have worked. You can see all the individual fibers that are running. You can see the cells that are being trapped. So all this comes together to create that clot, to prevent blood loss. But eventually, you've got to get rid of it. That's fibrinolysis. Lysis is breaking, fibrin breaking. In fibrinolysis, it usually starts within 2 days. It might even start the very next day. Depends how the body's working. Now, plasminogen in the clot is going to be converted to plasmin. So this was already built in. This was there when you built the clot. That plasminogen will be converted into plasmin. The purpose of plasmin is a fibrin digesting enzyme. It's meant to break down the fibrin. As you break down the fibrin, you're breaking down the clot, which is good because your body's trying to heal and you've got to replace that clot with the tissue that should be present, or fix the vessel that was damaged, or whatever else needs to be done. You're working on that as you go through. So plasmin is a fibrin digesting enzyme. Now, how do you prevent yourself from clotting if you don't want to clot? Let's say you don't have any damage. There's no breaks, there's no problems. What you have is the smooth endothelial lining. Think back to histology. Simple squamous epithelium. The simple squamous epithelium tissue lines the inside of your blood vessels. It's perfectly smooth. There's really no place for things to catch onto to form a clot. So that helps one way. You have antithrombic substances like nitric oxide and prostacyclin. We've mentioned prostacyclin. It helps prevent clotting. So again, trying to make sure you do not clot in your blood. Vitamin E quinine. This one is an anticoagulant. Again, preventing clotting. The whole goal is you don't want to clot your blood unless you have a reason. You damage your vessel, you have a cut, something happened. So this is all preventing a clot from occurring. If it's all working perfectly, you don't form a clot. Unfortunately, it doesn't always work perfectly. That's the idea of a thrombus. Now, a thrombus is when you have a clot that is developing and persists in an unbroken vessel. So there's no damage, no trauma, but for some reason in that vessel, a clot forms and it stays there. That can become problematic because it can impede blood flow and slow it down, create turbulence, increase pressure, or simply stop blood flow altogether. The second one is an embolus. Now, an embolus is just like a thrombus. In essence, it is a thrombus, but the thrombus broke free. So an embolus now is floating freely in your bloodstream. This can become potentially problematic because as this clot is floating in your blood, if it finds a more narrow vessel in the lungs or in the heart or in the brain and makes a clot and blocks it, you might end up rupturing a vessel there, which can become life-threatening potentially. So an embolus, if it's a large enough size, floating freely, can cause some pretty severe problems. Thankfully, our body tries everything it can not to allow either one of these to occur. That's why we have so many anticoagulant factors. We have so many things trying to prevent the clotting of the platelets. And then for a quick summary here, we're looking at the red blood cells, the erythrocytes, about 4 to 6 million per cubic millimeter, gas transport, oxygen and carbon dioxide. Next up, the grouping of the leukocytes, 5 in total. Leukocytes about 5 to 10,000 per cubic millimeter. We'll start with the neutrophils. Neutrophils are for getting rid of bacteria. So if you have a high count of neutrophils, it's probably an early bacterial infection. You then have the eosinophils. Eosinophils, you're looking at basically doing anti-parasitic worms and dealing a little bit with the antigen-antibody complexes. Then you have the basophils. Basophils are promoting inflammation. They're going to have histamines inside their granules. And from those three, we can move on. You have the lymphocytes. Remember, lymphocytes come in 3 different types. We have the natural killer cells. We have the B cells and we have the T cells. We then have the monocytes. Monocytes become macrophages. They're meant to seek out and destroy. If you have elevated levels of monocytes, it's been a long-term infection. And the last thing is the platelets. Platelets coming from megakaryocytes, 350 to 500,000 per cubic millimeter. They're meant for clotting. So trying to prevent blood loss. So a very quick overview of what the formed elements were again. So those are your formed elements, finishing off there with the thrombocytes.